Every single second, the modern global internet continuously routes millions of complex, variable-length data sequences across vast physical and geographical boundaries. To maintain this continuous flow, networks rely on the network layer, layer 3 of the OSI model. This layer abstracts physical cabling and wireless frequencies into a single logical addressing scheme using IPv4 and IPv6. When we look inside the architecture of a modern router, we see it operates on two separate planes. Down below is the data plane, and above it sits the control plane. The data plane executes the physical movement of the packets. If a packet exceeds the interface's maximum transmission unit, this layer fragments it. It queues traffic based on quality of service priorities and pushes the data out the appropriate physical port. But the data plane only acts on instructions. It requires the control plane. Here, dynamic routing protocols continuously share information with neighboring routers, calculate the most efficient network paths, and update the routing table, dropping those paths down to the forwarding layer. Isolating the routing logic from the physical forwarding means network hardware can instantly redirect traffic around severed links or sudden congestion without waiting for a human administrator to intervene. Dynamic routing protocols like RIP, OSPF, and BGP function as highly tuned algorithmic engines. They are built to process raw topological data into optimized paths in fractions of a second. The engineers who initially drafted these standards prioritized global reachability and hardware efficiency. Strict security was a secondary concern. Consequently, these protocols operate on implicit trust. A router simply assumes that any topological update it receives from a neighbor is mathematically accurate and administratively authorized. This profound reliance on implicit trust creates a massive foundational vulnerability. If just a single neighboring router provides false routing data, whether through error or malice, the entire control plane will propagate that error as truth. To diagnose a broken link or secure a routing domain, a network engineer must first understand the distinct algorithmic logic each protocol uses to view the network. For routing within a single organization or autonomous system, administrators deploy interior gateway protocols, or IGPs. Early distance vector IGPs use the Bellman-Ford algorithm, evaluating only metric distance and direction. Operating by rumor, they never see the complete topology. When a link fails, neighbors blindly pass outdated calculations back and forth, causing destructive routing loops. Modern enterprise networks solve this by using Link-State protocols, primarily OSPF, which replace Bellman-Ford with Dijkstra's shortest path first algorithm. Link-State routers flood Link-State advertisements, passing topology documents to assemble a complete, synchronized map, the Link-State database. Because every router holds the exact same map, a link failure triggers an immediate update, and each independently recalculates a loop-free path. This guarantees topological accuracy, but running the shortest path algorithm across a massive synchronized database consumes more memory and CPU power than distance vector routing. If a link-state network grows too large, a single unstable connection forces hundreds of routers to continuously recalculate the algorithm, eventually exhausting their hardware resources. OSPF scales through hierarchical compartmentalization, dividing the topology into specific zones connected by a central backbone, Area 0. When a local link state changes, the protocol strictly confines the resulting advertisements to the specific area where the event occurred. Area border routers maintain boundaries between these zones, acting as computational firewalls. They absorb internal updates, summarize the complex local changes into a single Type 3 advertisement, and forward only that efficient summary into the backbone. Isolating topological chaos within specific subregions allows enterprise networks to expand without overwhelming the processors on individual routing hardware. In this topology table, the algorithm evaluates a composite metric of bandwidth and delay to select the optimal active path, labeled the successor. Crucially, the protocol also pre-calculates mathematically loop-free backup paths, storing them dormantly as feasible successors. When the primary link drops, EIGRP does not flood the network. It immediately flips to this pre-calculated backup path. EIGRP proves high-speed convergence can be achieved through localized pre-computation rather than brute force mapping, reducing the hardware burden on the routing core. Internal enterprise scaling operates under different constraints than the global internet, where massive, distinct corporate and government networks must interface. To connect these autonomous systems, the internet backbone relies exclusively on the Border Gateway Protocol, or BGP. BGP is a path vector protocol. It does not track individual physical links. Instead, as we see on this global map, a routing update builds a sequential history, appending the specific autonomous system numbers it traverses to an AS path list. Because peering routers often sit on different physical networks, BGP establishes a reliable, manually configured TCP connection on port 179 to exchange these path updates. The path history itself provides the mechanism against routing loops. If a BGP router receives an update containing its own autonomous system number in the path history, it silently drops the update. By discarding simple speed metrics for complex path attributes, BGP allows service providers to dictate traffic engineering based on commercial agreements and strict administrative policy. The control plane logic governing these protocols is highly fragile. Minor configuration errors can prevent routers from forming neighbor adjacencies, resulting in complete network isolation. In OSPF, neighbors transition through strict operational states. This flowchart demonstrates a peering session stalling completely, freezing at the ExStart phase. This failure points to mismatched maximum transmission unit sizes. Because interface capacities don't align, routers cannot fragment and reassemble their large database descriptions. EIGRP exhibits a different failure mode, known as stuck inactive. This occurs when a route drops, no backup path exists, and the algorithm freezes while actively querying adjacent routers for an alternate path. A stuck inactive event typically indicates that downstream links are heavily congested or that a router's CPU is too exhausted to generate a query response. While Layer 1 testing checks the physical cable, analyzing these protocol-specific state machines is essential for isolating logical stalls that occur entirely within the control plane software. Operational misconfiguration causes accidental isolation, but the core assumption of implicit trust allows for malicious exploitation, exposing the danger of prioritizing reachability over identity verification. A BGP route hijack weaponizes trust. On this map, an unauthorized node broadcasts a fake path announcement, claiming ownership of a target prefix. The routing table blindly accepts the update, instantly redirecting legitimate traffic away from its true destination, funneling it to the attacker. Internal protocols face parallel threats. A compromised router can inject crafted Type 1 advertisements to poison an OSPF database, or manipulate EIGRP metric values to silently force sensitive traffic through an eavesdropping server. Without an external source of validation, the decentralized efficiency of dynamic routing actively facilitates catastrophic data interception and denial of service. Securing modern network layers requires completely abandoning implicit trust. Administrators must implement a multi-layered defense strategy focused on explicit authorization. The solution for validating BGP is RPKI. On our map, the border router intercepts the rogue announcement and compares it against a cryptographic certificate. Because the attacker lacks the private key, the announcement is flagged invalid and discarded, protecting the routing table. At the local level, engineers implement defense in depth. Control plane policing protects the processor, while MD5 and SHA authentication prevent rogue hardware from forming adjacencies. Constructing a resilient network requires moving beyond the efficiency of path determination and implementing the technical mechanisms required for explicit cryptographic authorization.